Hello everyone and welcome back to Terabyte. We are Geek Gurus Union and this is our Demo 2 video. So last time we introduced Terabyte, a crop prediction system that provides data-driven solutions to farmers. In this demo, we'll provide an update on our documentation, machine learning model, testing and overall progress. Talking about our quality requirements, the 5 main ones identified were performance, testability, efficiency, compatibility, and usability. Talking about performance, performance is considered a crucial underlying factor for our system, highlighting the importance of processing power and all-round data analysis capabilities. On the front-end side, effective and rapid rendering is crucial for real-time statistics provided to the end user, while being backed by a solid backend system with a rugged API. Our quantification identified for performance was that the machine learning model should be trained within 5 minutes, our app loading time should be under 10 seconds, and then our API responses should also be under 5 seconds. This ensures that farmers have a system that is reliable and performance heavy. Talking about performance, performance is considered a crucial underlying factor for our system, highlighting the importance of processing power and all-round data analysis capabilities. On the front-end side, effective and rapid rendering is crucial for real-time statistics provided to the end user, while being backed by a solid backend system with a rugged API. Our quantification identified for performance was that the machine learning model should be trained within 5 minutes, the app should load within 10 seconds, and the API responses should be less than 5 seconds. This ensures farmers have a system that is performance heavy and they can make more AI-driven decisions.
Since our last demo, we've written more extensive unit tests for all our components. For our backend, we made use of PyTest, and we've written integration tests to test the compatibility between our components. To quantify our test, we've generated a code coverage report to indicate how much of our code has been tested to reduce the risk of undetected issues.
Because we run a sophisticated service in the background on a constrained budget, having a system that avoids wasting effort, money, and time while performing a specific task is crucial. To see the efficiency of our system, we have used the graphs provided on our DigitalOcean Droplet dashboard, which shows us the budget, resource utilization, and response time. We also tried timing our function calls and output for our machine learning model as much as possible, and we also report our analytics to a CSV file to analyze any bottlenecks that may occur.
For compatibility, the app should be designed for easy installation on a variety of devices commonly used by farmers. The app should be configured for automatic updates over Wi-Fi whenever possible. And then we had a few key quantifications, such as making use of a PWA to ensure offline capabilities, providing a consistent user interface by using component libraries, fetching new data when connected to the internet by setting up runners that will periodically check for internet connection, and lastly, saving new data temporarily while the app is not connected to the internet by making use of local storage.
For our fifth and final requirement, the system should use weather, soil, and historical data to help the farmers predict crop yields and success. It is designed to be user-friendly and enjoyable for farmers to use. We quantified this by providing a clean user interface with user-friendly navigation. We ensured consistency in the design by providing the same consistent styling across the app. Talking about usability, let's jump into the machine learning model. So for our machine learning model, we did some pre-processing on images. We used that to extract data, make a mask from where crops would usually grow, and then export that into usable and informative statistics. We then used exploratory data analysis to perform correlation tests and compare the data visually against each other. We used models such as the correlation matrix plot and the linear regression model. We then imputed the values with the k-nearest regressor library from scikit-learn to fill up the missing data whenever possible to have as big as possible data set. The model itself is a long short-term memory model that is a RNN that suits best when working with sequential data. As opposed to other RNNs, the LSTM can keep data from long ago in memory. We use both TensorFlow and scikit-learn to help training with the model. As you can see on the right hand side, we currently have a test train split with 2080, and then we run 250 epochs with a batch size of 24. At the moment, we can also cater for any crop available. That ranges from soybean to wheat to maize and even certain nuts as well. For our complete model layout, we describe this by having a input set. This is from various locations, including SAGIS, FAO Stat, USGS, the World Bank, and University of East Anglia. This all comes down to one dataset from where we train our generic model, impute for missing values, and then expect the user to enter their manual reading of data, from where we would then train a personalized model, store that in the database, and then display the predictions. So for our actual unit and integration tests, let me show you how it gets done. So right here we have our unit tests that are runnable from both the terminal and from GitHub itself with automated workflows. As you'll see, most of the tests pass. This concludes our unit testing. I will now show you the Postman integration testing. As you can see, the majority of them passes. I'll now hand over to Saeed to talk about the presentation layer.
Yeah, some of our decisions for the technologies we use on the presentation layer. We decided to use Vue because it's easy to use, it's high performance and efficiency. We made use of Tailwind CSS to ensure consistent design across the whole application. Vitess is a fast unit testing framework for Vue apps, so it naturally was our decision to use Vitess for our front-end unit tests.
Then for our data layer, we decided to go with PostgreSQL. PostgreSQL is a powerful open source relational database system with a few pros that I can name for you, such as advanced features. PostgreSQL supports complex queries and foreign keys and triggers and such. It is extensibility, performance optimization, a large and active community with plenty of documentation, and high compliance with SQL standards, ensuring portability and compatibility.
For the logic layer, we went with TensorFlow, which is also an open source machine learning framework from Google, which is well suited for building a crop prediction system using LSTM and KNN networks. It is very flexible and scalable, enabling an efficient model development and deployment across different platforms. Some of the pros include that it is highly flexible and robust. It can easily scale to handle large data sets and is compatible with a lot of languages. Some of the cons is the training for the LSTM. It can be really resource intensive and requires quite a bit of computational power and memory. This is especially disadvantageous because our VM that runs on limited resources. Continuously training a model requires effective resource management to reduce time spent waiting for the training to complete. We also went with scikit-learn, which is a popular Python library for machine learning that simplifies data preparation. It is easy to use. The library provides a wide range of pre-processing tools. And it also includes robust tools for model selection and evaluation metrics. Scikit-learn is not designed for deep learning. While it is efficient, it may struggle with very large data sets or extremely high dimensional data compared to other libraries. We also used R, which is a programming language for statistical computing. It comes with a collection of packages for data manipulation and visualization, and many more. It is specifically designed for statistical analysis, making it an excellent choice for detailed and complex EDA. Some of the cons is that it's quite slower than some of the other models that are out there, and it has a steep learning curve, but luckily we have sorted that problem out. And we also went with Fast API, which ensures efficient API development with smooth data exchange, and reduces development time with automatic documentation and code generation. Some of the cons is that it is a relatively new framework compared to others. And then lastly, we went with PyTest, which is efficient for unit testing for the backend code, which helps us catch bugs early in development, but it may require additional setup and configuration compared to simpler testing frameworks. Okay, so what's next? Our next iteration will improve upon the MVP by expanding with real-time capabilities such as forecasts, a personalized machine learning model, a PWA, security, and next-level wow factors. Thank you for watching this demo, and we hope to hear from you soon.